Hi everyone, welcome back. In this video, we're going to talk about word arrangement. So word arrangement is a very specific type of combinatorics questions that's usually tested that involves multiple different techniques and a solid understanding of both combinations and permutations. So in this video, we're going to look through different types of word arrangement problems to see what kind of techniques they require and how can we approach the problem solving of each example. So the first question here involves permutation. So we're looking for all the distinct arrangements that we can make out of the word range. So if we look at range, there's RANGE, 5 letters without any repetitions. So if we have anything that's arrangement where order matters and there's no repetitions, so that means it's a simple permutation questions. So we're permutating 5 letters and the formula would be 5 factorial, which would be 5 times 4 times 3 times 2 times 1. And which will give us a 120 as answer. This is the first way to understand this, which is essentially using the formula directly, which is n factorial for permutating n distinct items where order matters. And the second way to understand this would be if we have 5 letters, rearranging all of these letters into a 5-letter word. So we're using all of them. So if you have a 5-letter word, the first position, we have 5 possibilities. We have 5 different letters to choose from range. And the second position, because we have already chosen 1 letter for the first position, so we will only have 4 letters left for the second position. And for the third position, we will have 3 letters left because we have already chosen 2 letters to place into the first 2 positions. And so on. We will logically come up with this expression right here. So it's the same thing as 5 factorial, but this explains why it is 5 factorial. So this will give us an answer of 120. So there are 120 distinct arrangements of 5-letter words that we can make out of a range, R-A-N-G-E. The second type of question is a range committee. We need to use all of the letters and to see how many distinct arrangements can be out there. So we have CO, 2 M's, I, 2 T's, 2 E's. So in total, we have 9 letters. So we're making a 9-letter word. But this question, we need to recognize that we have some repeating letters. So when we are permutating n items, and within this n items, we have some repeating items. So we need to use the technique of reducing overcounting for this example. So how do we do that is we divide it by all the items that's repeating factorial underneath as a denominator. So this would be the formula right here. And a simple example would be if we're arranging REE, these 3 words, we could use 3 factorial and we will get 6 because there are 3 letters. However, we have 2 E's right here. So when we are using 3 factorial, we are assuming all these are different. So for example, if we have 3 letters, 3 positions, the first position we can choose R to put in there. And the second position, since we already chosen R, we have E and E left. So we can put a E in here. And the last position will be the other E. However, for 3 factorial this way, we're assuming that these 2 E's are actually different to each other. So this R, for example, if we have a R, let's say this E is green. So 3 factorial treats R blue E green E is different than R green E blue E. However, they're the same e's, so REE is only one possible permutation of the three letters REE. So we need to divide it by the possible ways that the two e's can arrange themselves. So we divide it by 2 factorials, and we will have 3. So this is actually all the ways that we can arrange REE into distinct 3-letter words. And we will see that that is true because when we are arranging REE, the 3 possible ways that we can arrange these 3 letters are REE, ERE, and EER. All the other possible ways are repeating from these 3 fundamental ones. So this is why we come up with this dividing to reduce overcounting idea. So how do we find the ways? It would be 9 letters, so we do 9 factorial, but then we divide it by 2 m's, so we divide it by 2 factorial to reduce the overcounting of these 2 m's. 2t, so 2 factorial again, and 2e, 2 factorial again. So by doing this, we can reduce the overcounting problem by a division. So it's essentially, so this would be the answer. This is the expression that we could use to express the answer. We could also simplify the expression to, this is 4, this is 2, to this. So 9 times 8 times 7 times 6 times 5 times 3. So this would be the answer to this question where we're arranging committee. So this is how we can deal with repetition in permutation. The next kind of question is when we're still arranging letters in a word, but this time with some specific restrictions stated in the question. So the first example right here is we need to arrange the word range, but this time still a 5-letter word, but starting with a vowel. So we have a specific restriction or condition right here. And normally there's not a one-size-fits-all approach to all of these restriction questions. We need to deal with the conditions specified in the question stem case by case. So in this question, we're arranging a 5-letter word and using all the letters here, and there's no repetition in word range, so which is good. And we need to start with vowel, means that in the first position, this position can only accept vowels. So let's say we have, if we look back into the word range, we only have 2 vowels in this words, A and E. It means that on the first position, we only have 2 possibilities to choose from. We can either do A or do E. No other possibilities. We cannot put R or N or G in the first position. And so we only have 2 possibilities. And on the second, starting from the second position, we can think about this way. We have 5 letters. From A and E, we choose either one of them. So we would have, for example, if we choose A, then we would have R and G and E left, and we can do either one of them, either one of the 4 to put into the second position. And similarly, if we used up E on the first position, we can still have 4 different possibilities to put onto the second position. So on the second position, we will have 4, and then 3, 2, 1, which is the same logic right here. So if we have 4 distinct letters, so these 4 positions are actually 4 distinct letters permutating. And they're all different. So no need to consider for repetition. So this is essentially 4 factorial. So it's 2 times 4 factorial, which will give us a 2 times 24, which is 48. So this is the total ways that we can arrange range into a 5-letter word starting with a vowel. Next is another kind of commonly appearing restriction for word problems or any other kind of combinatorics questions, which is bundle question. So we're trying to bound some items together in all the permutations. So we are arranging the word red hawks, but vowels must be together. So if we look at this word, and by the way, this question, we're still using all the letters in the word. So we look at the word and we can see there are quite a few vowels in the word actually. We have E, we have A, and these are the two vowels. So all the other letters are different, so there's no repetition that needs to be considered into this question. If they must be together, the way that we do this kind of question is we just bound the two vowels together, and we'll consider this as a whole unit for permutation. And we just put all the other letters down, which is like this. So in fact, equivalently, we're essentially permutating 1, 2, 3, 4, 5, 6, 7 items. So the formula says n factorial. So the way that we can permutate 7 letters or 6 letters and 1 bundle, which we consider that as a unit or a letter, is 7 factorial. And then we need to consider that for each possible permutation of these 7 items, this E and A within the bundle can also switch place, creating a new permutation, a new arrangement of the letter. For example, if we have R, the bundle here, DHWKS, this is one of the many possible permutation that we can make. There are actually 2 possibilities for the bundle. We have EA or we have AE. So the first one is READHWKS, and the second one is DHWKS. So we actually have 2 possibilities within that bundle. So in fact, we will have 7 factorial times 2. This will be our final answer. And you can definitely use your calculator or go online and find the numerical value of this expression. But this will be how we approach bundle questions, this kind of typical conditions that's usually tested. The next type of example is casework. So this is probably one of the most challenging example that we're going to look at in this video. So the question says, arrange the word committee starting and ending with vowels. So the condition is very similar to what we have been talking about earlier, just now, which is finding the vowels and placing the vowels in specific places. And this time, we will do 4-letter word instead of using all the letters in the word committee. So we can definitely start by trying. Doing something similar to what we've been doing. So we have 4-letter word, and if we look at this, we have O, I, and 2 E's as vowels. So we can put a little agenda here, help us to visualize. So we have O, I, E. So we can definitely say that, we need to put vowels on these 2 positions only. So on the first position, we can do either one of O, I, E, E. So we actually have someone will say it's 4 possibilities, but I'll argue that there are actually 3 possible different letters here, O, I, or E. And then on the last one, the question actually says with different vowels. So it needs to start and end with different vowels. Therefore, we have chosen one of, for example, we've chosen O. So we only have 2 possible vowels, I or E, left to put on the final position. And someone will say, it's a simple question because we only have 2 positions in the middle, and we've chosen 2 vowels, so we only have CMM, TTEE, for example, left, and we can just put them in. We can do 1, 2, 3, 4, 5, 6, 7 letters, and we can just choose two from the 7 letters and just do a permutation for the two possible. Because we can switch the positions in the middle, so that 2 letters could generate 2 different possibilities for each pair of letters that we chose here. So this will just give us answer and we're done. However, there's a twist to this question right here. This 7 choose 2 doesn't work out very nicely actually, because these items are actually not distinct. We could choose CM or MT or whatever, it doesn't matter. But we will count MM twice. And we will count TT and TT as different. So there's definitely some overcounting here. But not everything is overcounted. So we can't just simply divide 7 choose 2 by some number to reduce the overcounting problem in this question. So this method actually doesn't work out very nicely. So what we need to do here is we gotta do caseworks. And casework is such a delicate, a nice approach that we could use to deal with this kind of question. And it is not super challenging, but it requires some endurance and make sure your mind is highly tuned in when you're doing caseworks, because it's super easy to just forget about a case or just mess up somewhere in between. So we need to recognize that we need to still start with the 4-letter thing, that we only have essentially 3 possible pairs of vowels that we can put on the first position and last position from O, I, E, E. So the first possible way is that we can use O and I to put on the first position and last position. So we can either do OI or IO. And the middle parts, we will worry about them later. So there are actually 2 possible ways that we can use OI as the 2 vowels, starting and ending vowels for this 4-letter word. The second case is where I can use I and E as the first position and last position. And again, I can do IE or EI. So 2 possibilities. And lastly, I can do OE, which is again, I can do OE or EO on the first and last position. So 2 possibilities for that as well. And since we need to start and end with different vowels, that means EE doesn't work out very nicely. So by doing these, we already considered the vowels. But the difficulty lies in the next step, because as we said, it seems like 2 times 7 choose 2 doesn't work out very nicely. Then what could we do? The answer is doing subcases. So we can make even more smaller cases within these 3 big cases. So the first small case that we can do is to say that the middle 2 letters, are actually same. So same middle letters. And on the contrary, we can do different middle letters. And because these 2 cases are mutually exclusive, they can never happen at the same time, which means we have actually accounted for all the possible arrangements for the middle 2 letters. So essentially, we're separating the CMMT cases and MMTT cases. So we're separating these 2 into 2 categories and account for them differently to make sure we're not overcounting anything. Instead of doing something like 7 choose 2, where you're just forcefully combining these 2 very different cases and messed up. And similarly, for each other cases, it's the same logic. I can do same middle letters and different middle letters for the two for the two subcases within this big case. And how do we do that is we can simply list out what letters do we have left after we used up the two vowels that we pre-assigned. And then we can see, oh, what can I do to make sure the two letters in the middle are the same? Or what can I do to make sure that the two letters in the middle are actually different? So let's start with the top big case right there. Okay, so our word is again committee, and we have already used O and I. So the letters that's left, I will use green, is C, M, M, T, T, E, E. So if we use two same letters for the middle two positions, we only have three different cases, which is MM, TT, or EE that are available in this small letter repository. If I want to do different middle letters, then I could use a multiplicative principle where on the first position I will have 1, 2, 3, 4 different possible letter choices. So CMTE. Because the two letters are different, so we could just simply ignore the doubling of letter M, letter T, and letter E because we'll never use them. So I will have 4 possible letter choices for the second position right here, and then 3 choices for the next one. So in total, I will have 12 possible arrangements of the middle letters. And since these two are parallel subcases that they never happen together, they're mutually exclusive. So the total cases that will be entailed by these two subcases are 3 plus 12, which is 15. And we said for whatever cases that arrangements that will emerge from these two subcases, we need to multiply a 2 to account for OI and IO. So essentially, the total cases that are entailed in big case number 1 is actually 2 times 15, which is 30. Next is the second big case, which is IE. So IE, we look at this committee, the word. If we chose IE, we will have COMMTTE. And if we want to do same middle letter, again, we only have 2 possibilities because we can only do MM or TT. And if we want to do different middle letters, then again, for the 4 letters, for the middle 2 positions, I have COMTE, 5 different letter choices. And then if I've chosen one of them, then I will have 4 letter choices left for this next position. So in total, I will have 20 different possibilities. And if I add them together, I will have what is entailed by these two subcases. And then I multiply by 2, which I will get a 44. That is the big case number 2 number. Finally is OE. So if we chose OE from the word committee, I will have CMMITTE. And if I want to do same 2 middle letters, I still only have 2 possibilities because I can only do MM and TT. And if I want to do different middle letters, I can have a CMITE. 5 different letter choices for the second position, this one. And I will have 4 different letter choices for the next position, so in total 20. And since again these two subcases are mutually exclusive and parallel to each other, the total cases that entailed by the 2 small subcases are 22, and then I can use 22 multiplied by 2 to account for the order of OE. I will have 44. And then what we can do to successfully solve this big question is essentially to tally up the three big cases. So the total number would essentially be 30 plus 44 plus 44 is here, here, and here. And it will be 74 times 44, which will be 811. So the total number of all the possible arrangements of the words committee of four-letter words that we can arrange from the word committee, starting and ending with different vowels, are actually 118. And if we do the 2 times 7c2, this will give us a much, much bigger word. We can actually try. This would be equal to 2 times 7 times 6 times, actually smaller, 2 times 1, which is 2 times 21, which is 42. So it will only give us 42, which is way off from the actual answer, 118. So this question would be considered as quite challenging comparing to other typical combinatorics questions, because this involves some careful case classification and operations of fundamental combinatorics principles and theories. So in total, we will have 6 smaller cases to consider, and in total, it's 3 big cases. And we all start from the condition of the question. I hope this video is helpful for you to understand what kind of word arrangement problem can there be on the test, and how can you approach to these kind of different types of questions strategically and with some thoughts in prior. Thank you for watching.